Have you ever wondered what it takes to create a space so clean that a single particle could shut down production or ruin an entire batch of medicine? Clean rooms look simple from the outside, but behind the scenes, they're constantly fighting an invisible battle, one that relies on engineered airflow, strategic filtration, and pressure control to keep contamination out. Imagine a place so clean that a single speck of dust could destroy an entire batch of medicine or ruin a computer chip. That's the world of clean rooms, ultra-controlled environments designed to eliminate contamination, protect products, and ensure quality in industries like pharmaceutical production and semiconductor manufacturing. In this first video, we'll break down how clean rooms work, why airflow control is so critical, and what engineers and technicians need to know about pressure cascades and cleanliness classes. In the air around us, inside our homes, offices, and factories, millions of microscopic particles are constantly floating unseen. These include dust, skin flakes, fibers, pollen, and tiny droplets that drift effortlessly through every ray of light. Most of the time, we never notice them, until a beam of sunlight shines through a window and suddenly reveals an entire galaxy of particles dancing in the air. While this level of contamination is harmless for daily life, it's completely unacceptable for environments that produce pharmaceuticals or microchips. In those industries, even a single particle could contaminate a sterile drug or short-circuit an integrated circuit worth thousands of dollars. That's why these critical facilities rely on clean rooms, controlled environments designed to remove nearly every trace of airborne contamination. What is a clean room? A clean room is a specialized environment designed to control airborne particles, temperature, humidity, and pressure, all to protect sensitive manufacturing processes. These spaces are used in pharmaceutical production, semiconductor fabrication, biotech labs, and medical device manufacturing. Anywhere contamination can't be tolerated. Medicines, vaccines, and sterile injectable drugs must be produced in environments where even a tiny particle or microorganism can compromise their effectiveness, stability, or sterility. If a clean room is not properly maintained, or if contamination enters the production process, it can lead to unsafe products, ineffective medication, costly recalls, regulatory violations, and potential harm to patients. In biotech labs, clean rooms are essential because they provide a controlled environment where sensitive biological experiments, cell cultures, genetic engineering work, and diagnostic processes must be protected from contamination. If the environment is not clean, contaminated samples may lead to inaccurate data, failed experiments, damaged cell lines, and even the risk of introducing harmful pathogens or cross-contamination between projects. In semiconductor fabrication, clean rooms are vital because computer chips are built at microscopic and nanoscopic scales, where even the smallest particle can ruin an entire wafer. Dust, skin flakes, or airborne contaminants can settle on silicon surfaces during lithography or etching and cause defects, shorts, or complete failure in the circuitry. If the environment is not kept clean, a single particle can destroy millions of dollars worth of product, reduce manufacturing yields, cause performance issues in finished chips, and lead to costly production delays. Clean rooms ensure the precision, reliability, and consistency that modern electronics depend on. Unlike a typical office or warehouse, clean rooms are engineered to remove microscopic contaminants, things like dust, bacteria, and even vaporized chemicals that could compromise a product's quality or safety. How are clean rooms classified? Clean room classification. Clean rooms are classified by the number of microscopic particles allowed in a single cubic meter of air, following the ISO 14644 standard. To put that in perspective, the air we breathe every day contains millions of particles. But an ISO Class 3 clean room allows only about 35. As the classification number increases, the allowable particle count rises dramatically. In our next visual, you'll see 5 cubes representing different ISO classes, each filled with an increasing number of particles, from ultra-pure to nearly unfiltered. This comparison helps illustrate the incredible difference between the air in your home and the air inside a pharmaceutical or microchip clean room. The cleaner the process, the tighter the air quality requirements. Let's visualize what these classifications really mean. As we move from left to right, the air becomes less clean, showing how particle counts increase with each ISO class. The first cube represents an ISO Class 3 cleanroom, allowing only about 35 particles per cubic meter. This is the air quality required for advanced microchip lithography or aerospace optics, environments where even a single particle could destroy a product. The next cube, ISO Class 4, permits just over 350 particles per cubic meter, still incredibly pure compared to normal air. You might find this level in the assembly zones of high-end semiconductor fabs or specialized pharmaceutical research areas. Moving up to ISO Class 5, we now allow roughly 3,520 particles per cubic meter, about the same as the air near a sterile filling line in pharmaceutical manufacturing. Still, this is a fraction of what's in ordinary indoor air. At ISO Class 6, particle counts rise to about 35,200 per cubic meter. This level might be used for support areas adjacent to more critical clean zones, where equipment is prepared or materials are transferred. Finally, ISO Class 8, allowing around 3.5 million particles per cubic meter. Even this is far cleaner than typical indoor air, which can contain more than 35 million particles in the same space. From left to right, the difference is astonishing and essential for producing safe medicines and flawless microchips. Why are pressure and airflow so critical, and what engineers need to know to design, maintain, or simply understand these fascinating spaces? Air changes in clean rooms explained. One of the most critical factors in controlling the cleanliness of a clean room is the amount of clean filtered air moving through it. This concept is called air changes per hour, or ACH. And the cleaner the room needs to be, the more air changes we deliver, sometimes hundreds of times per hour. What air changes do? Air changes exist for one simple reason: to remove particles faster than people and processes create them. Even in full clean room garments, a person standing still can release around 100,000 particles per minute. Walking can generate 1 to 5 million. Brisk walking can exceed 7 million. And uncontrolled movement or horseplay can release tens of millions, often over 100 million particles per minute. Without continuous air replacement, these contaminants would stay suspended long enough to settle onto critical product surfaces. High air change rates sweep these particles away, dilute them, and prevent them from accumulating inside the cleanroom. Why higher cleanroom classes require higher ACH? As you move into stricter cleanroom classifications, from ISO 8 and ISO 7 down to ISO 6 and ISO 5, the particle limits become dramatically tighter. To meet those requirements, we must increase the air change rate. For example, an ISO 8 cleanroom may only need 10 to 20 air changes per hour, but an ISO 5 area typically needs between 240 and 360 air changes per hour. At 60 air changes per hour, that's the entire volume of room air being replaced every minute. Achieving those high air change rates requires more than just moving more air. It requires a larger percentage of the ceiling to be covered with HEPA or ULPA filters. Lower-grade clean rooms might have only 5 to 15% of the ceiling dedicated to filtration, with the rest filled by lights or solid panels. As cleanliness levels increase, so does the number of filters, and the percentage of ceiling coverage grows from 30 or 50%, all the way up to 60, 80, or even 100% in ISO Class 5 cleanrooms. When the whole ceiling becomes a field of filters, the airflow changes character. Instead of turbulent air swirling around the space, the room now has a smooth, uniform downward flow, called laminar airflow. This downward sweep acts like an invisible protective curtain. Any particle released by personnel or equipment is pushed toward the floor, immediately captured by low-level returns, and sent back through HEPA filtration. So, the purpose of air changes and high filter coverage is not just to keep the room clean, it's to keep it continuously cleaned. Particles don't have a chance to accumulate. They don't drift onto product surfaces. They don't linger in critical zones. They are constantly removed, filtered, and replaced with ultra-clean air. In the end, air changes are the engine that drives clean room performance. The higher the cleanliness class, the higher the air change rate, and the greater the ceiling coverage of HEPA filters. This combination creates a controlled, predictable airflow environment that protects the product, the process, and the people, ensuring the cleanroom stays clean, no matter how many particles humans generate. Pressure cascades. One of the most important principles of cleanroom design is the pressure cascade. Each room is pressurized slightly higher than the one beside it, so air always flows from cleaner to less clean spaces. That means when a door opens, clean air pushes out dust or contaminants, preventing them from sneaking in. For example, in a pharmaceutical facility, the sterile filling room might be held at plus 0.05 inches of water gauge, while the adjacent gowning room is at plus 0.03, and the corridor slightly lower. This creates a gentle but effective air barrier protecting the most critical zones. How are particles removed to achieve cleanroom levels? The heart of every cleanroom is its air management system. Cleanrooms use HEPA or ULPA filters to scrub the air, removing more than 99.97% of particles down to a fraction of a micron in size. In high-performance rooms, that air flows in a smooth, single direction known as laminar flow, sweeping contaminants away from the workspace. Air is constantly replaced, sometimes hundreds of times per hour, keeping the environment ultra-clean and stable. Air is continuously circulated through high-efficiency HEPA or ULPA filters that remove nearly every particle larger than a fraction of a micron. The air then flows in a precise pattern, often from ceiling to floor, to sweep contaminants away from work surfaces and equipment. Each zone within the cleanroom is pressurized slightly higher than the one next to it, ensuring that air always moves from cleaner to less clean areas. This cascading flow of filtered air creates invisible protective barriers that maintain product integrity and protect both the process and the people inside. The systems behind the scenes. Maintaining those standards requires precision engineering, from the HVAC systems that deliver temperature and humidity control to the building automation systems that monitor pressure differentials around the clock. Many clean rooms use airlocks or gowning rooms as transition zones and pass-through chambers for materials, all designed to minimize particle transfer. During commissioning, engineers perform airflow balancing, filter testing, and pressure verification to ensure everything performs exactly as designed. We'll cover these topics in the next video on clean rooms. Summary. Let's recap the key concepts that make clean rooms work. First, clean rooms rely on high air change rates, replacing the entire volume of air dozens, hundreds, or even hundreds of times per hour, depending on the classification. These air changes sweep away particles before they can accumulate or settle on critical surfaces. Second, the percentage of ceiling area covered by HEPA or ULPA filters increases as the cleanroom class becomes stricter. Lower-grade cleanrooms may use only a few filter tiles, while ISO 5 environments often use a fully filtered ceiling grid. Third, this high-density filtration creates a smooth, uniform downward laminar airflow that continuously pushes contaminants toward the floor, where they're removed by low-level returns. Finally, clean rooms maintain cleanliness through a combination of filtration, airflow direction, pressure cascades, controlled behavior, and strict garment protocols. Every part of the design works together to keep particles away from the product, even when people are shedding millions of particles per hour. If you found this video helpful, be sure to check out our HVAC and plumbing estimating spreadsheets to streamline your construction bidding process. Check out our HVAC, electrical, and plumbing construction forms to help you run your business, and explore our online courses for in-depth training.